This session that we're going to go through today is a deep dive into a feature of TCP called Selective Acknowledgement. I tend to walk around the room. I probably shouldn't do it too much with that there, but I'm going to walk around the room a little bit as well while I'm talking. I think this will reach. John Pittle is my name. I'll introduce myself some more in just a moment. This is what I'm hoping your agenda is for this session and why you came to the session today. Hopefully you've heard about selective acknowledgement. You want to learn more about it. We're going to deep dive into how out-of-sequence delivery can impact performance and how you can interpret that through selective acknowledgement. And hopefully you're interested in more about the things you can do with the Wireshark display filters and display capabilities to create custom views. We're going to dive into that a little bit as well. In terms of my agenda, I'm going to talk about some relevant RFCs, just going to make sure you know the numbers. We're not going to read them together. We're going to review some basics around TCP acknowledgement, then we'll introduce SACK. We'll look at some decode details. We'll look at some example illustrations to really cement the concepts of what does this field mean relative to traffic that's arriving at a host. And then I have a deep dive, something I call Adventures from the Field, which was a really interesting engagement I had a few years ago that is kind of fun to see selective acknowledgement in action. And then we're going to wrap up. So a little bit about me. I've been doing performance engineering for quite a while, protocol analysis in the ethereal days and certainly on into now. I love complicated performance issues. If it's the ones that nobody else can solve, that's the one that I'm anxious to be part of, right? Working with people, of course. And then the other most interesting thing about myself is I shaved, well, I mean many interesting things, but I did shave my beard off in 2003. So let's get started. So first off, just a note about the relevant RFCs that cover the behavior we're going to see today. So 793 is the granddaddy of them all. Anybody ever read 793? Yeah? It's not great reading, but it's important reading. It's really nice to see what the thought process was of how the early author, Postal, I think his name was. Is that right? Does that sound familiar, Postal? Yeah. How they set about to actually document the behavior that we could expect to see for a protocol that doesn't even exist yet. Kind of really interesting. We're going to focus on 2018. And I want you to know that there's an extension to selective acknowledgement documented in 2883. So those are the RFCs. If you want to research more about the behavior we're going to look at, these are the RFCs that cover those. So let's start with a review of some basic behavior. The way I do these sessions is I start with really basic fundamentals and then I build on them, so that we're comfortable with the foundation, we build on that, get comfortable with that, build on the next level, etc. So some basics here. So as long as packets arrive in the expected order, the default behavior is the receiver should ACK every other packet. Is everybody comfortable with that? That sounds familiar? You can change that behavior. If you wanted to, you could make it every fourth packet, every packet. Those are settings in the TCP stack, depending on the operating system. And here's the part that we're going to be focused on. If a packet arrives out of order, we have to change behavior. Now we have to ACK the packets that are out of order until we get every packet that's out of order, so that we can signal back to the sender, hey, I'm receiving something, but it's not what I'm waiting for. It's not in order. I did receive something, but it's not what I was expecting. Does that sound familiar? Pretty common? So far, so good? And the receiver will continue to do that behavior until the expected packet is received. So these are all kind of standard TCP 101 level concepts. So hopefully everyone is comfortable with that. Now, if the sender receives, I always have trouble with that wording. How can a sender be receiving? But I tried different words. This is the best I came up with. So the sender is sending, the receiver's signaling back, right, the ACKs. So if me as a sender, if I'm receiving back 4 ACKs in a row with the same ACK number, what we call a triple duplicate ACK, then it's time for me to retransmit that segment if fast retransmit is enabled on the sender side. So far, so good? Anything unexpected up here at all? These are the basics that we're gonna build on. So what we call the ACK actually has a very special name called the Cumulative ACK. Thank goodness we can just call it ACK, because Cumulative ACK is hard to say. It's a tongue twister, but it's important that we give it a name because we're going to introduce new names when we talk about Selective ACK. So the Cumulative ACK is in the TCP header, and this is a point that I think sometimes gets confusing and it's worth reinforcing. So whatever value we declare in that ACK field, it says this is what I'm ready to receive next. I've received everything up to that number -1 in the stream, and now I'm ready for this byte of the byte stream. And so the next packet that should be sent, once I get this ACK, would be a sequence number with that value. So far, so good still? So the word cumulative is important. We're going to see a new term in just a minute. So cumulative ACK is what's documented in the RFC. And I would like to ask, there's 2 promises that TCP makes as a protocol. 2 promises. So I'm going to ask the audience here, what's one of the 2 promises that TCP makes? Reliable delivery, and I'm going to add to that in order, in sequence. So the reliable part means I'm going to deliver the data to the application, the receiving application, in the right order, and it's going to be complete. Is everybody okay with that? What's the other promise? And I know I've read this someplace, so this has to be real. Sorry? Well, it is a connection-oriented protocol, yes, but there's a promise TCP makes. I promise to deliver in order. I promise to be reliable. So that's the reliable. The other thing I promise to do is not to overload the network. That's why we have that congestion window that slides, right? I promise if I believe as a sender that the network is not reliable or it's degraded, I promise I won't add to the problem. I won't overrun the network. So 2 promises, in sequence, reliable delivery, connection-based protocol, and I promise not to overrun the network. So cumulative ACK, those 2 principles are kind of key whenever you hear about congestion control, what we're going to look at here in a few minutes. Those 2 promises are always at the foundation. So let's introduce now Selective ACK, Selective Acknowledgement. So it came out with RFC 2018. And the idea is I want to inform, me as the receiver, I want to inform the sender that I have received something out of order. And I want to be able to declare which bytes of this, which stream bytes I have received that are out of order. Because really there's no need for the sender now to retransmit those. There's a piece I'm missing, but there's other pieces I have received. And we're going to walk through this in a lot of detail. Okay, so how do we implement that? So it's a new addition to the TCP options field of the header. And using that options field, we have some flexibility about how much we can fit into the options field. We can, in the case of SACK, we can fit up to 4 contiguous blocks of stream bytes that we've received out of order, as long as we're not using TCP timestamps. So if we're using TCP timestamps, that's going to take up space in the TCP headers field, options field, sorry. And so that only leaves us enough room for 3 SACK blocks. And we'll look at that in detail as we go through this. So it's implemented in the options field, which is really great because that means we didn't have to rewrite. We're compatible with systems that don't support SACK. It's in the options. They may process them, they may not process them. So how do we enable it? Well, it's on by default in most modern TCP stacks, so Linux, Windows, etc. In older versions of Windows, there were registry entries that you had to enable in order to turn on selective acknowledgement, as well as Windows scaling and some other options. But it's generally on by default nowadays. It's negotiated connection startup. We'll look at that in a minute as well. And if you were to look at the SYN and the SYN ACK package, you're going to see an option that says SACK permitted, which means I will process SACK if you send it to me. It doesn't mean get ready, I'm about to send it to you. It's really all about, it's all about me. It's what I'm willing to do. I'm willing to process it if you send it to me. And each side can independently choose whether or not they want it on. So the whole idea is we want better intelligence about what's being delivered, particularly the out-of-order bytes. Ideally, we're going to minimize the number of retransmissions. That's what we're trying to do with this. We're trying to minimize the amount of retransmissions on the network. And that third bullet is really an absolute key point. It will not necessarily change the way congestion control works in a host. It might not. It's quite possible, well, in the RFC, there's a lot of, if you've read RFCs, you'll find there's a lot of shoulds and mays, which is very different than a must. So a should and a may means you should do this, you may do that, but it's not obligatory. Me as an implementer, I could decide not to do the shoulds and the may. So it does matter what operating system you're running, what version of kernel you're running, what version of the OS that you're running. So when you're doing packet analysis with Wireshark, the way you're going to use the information that's provided in the SACK field is to help you determine how bad is bad. Like you can have a little bit out of order, or you can have a lot out of order. You can have blocks that are out of order and everything else is in order. There's very chaotic behavior when things go wrong in the network, particularly with firewalls and intrusion prevention and proxies, things in the path. So the idea is not whether or not you've had any out-of-sequence packets, but how much, how often, and how bad. And we'll see some examples of what bad looks like. Bytes in flight is really your guiding metric to tell if the application performance is impacted. So remember I mentioned the word congestion window. I'm hopeful most everyone here is familiar with the congestion window opening and closing based on network reliability. Congestion window opens, I can burst more. If there's instability, I have to close it and burst less because I have to protect the network. I can't add to an already unreliable network. That's one of the promises of TCP. If your in-flight data or bytes in flight stays high, meaning your congestion window is nice and big and open, wide, then you really don't have a performance issue. Because you're getting good bursting, you're getting good throughput, the sender's happy that the network is behaving, everything is good. But if you see in-flight data or bytes in flight, which is a Wireshark field, anybody use bytes in flight as part of your normal performance analysis? It's a really key, important field, yeah? So, but if bytes in flight is going down or hits 0, or you see TCP slow start, where the window goes all the way down to like one segment, now I got to start slow start all over again. If you see bytes in flight go down, then you want to determine if the problem is because of out of order. It could be packet loss, good old traditional everyday, the network is falling apart packet loss, but it could also be out of sequence packets, in which case the packets are arriving, but they're not arriving in the right order. Okay? And we'll see, like I said, we'll see some examples. So does anybody remember this date, April 19th, 2011? It's kind of a trick question, but I couldn't resist. So this is when SKYNET, if you've ever watched the Terminator series, became self-aware, so they say. Wireshark is self-aware about SAC. So Wireshark has some great capability around displaying, interpreting, filtering the SAC field. So we're going to look at some concepts in the SAC field around a count. How many blocks of SAC are present in the options field? We're going to look at the concept of left edge and right edge. We'll look at that in some detail. And you can display those in your columns in your decode summary. One of the best things about Wireshark. Many great things about Wireshark. That's one of the best. If your capture came from the sender, then you're going to see both retransmissions and duplicate ACKs. But if your capture came from the receiver, you're going to see dupe ACKs and out-of-sequence packets. And there's a session tomorrow that I hope you'll be interested in, comparing client and server behavior for various symptoms around performance. And we dive into that in a lot more detail tomorrow. So, quick look at the columns and quick look at the fields. So up here in the header, let's see if this will, yeah, good, okay. Up here in the header, we have our, what was this ACK called? Cumulative ACK, thank you. Saying that, hey, I'm ready for 14.771. I've received everything in order reliably up to and including 14.770, and I'm now ready for 14.771. But notice up here I've got a SAC count column, a left edge and a right edge. And my SAC count column says, but hey, there's some information in the options field describing data that I've received out of order. The left edge is this byte stream number and the right edge is this byte stream number. And if we drill down into the details down here, so not only have we received this in order, but I've also received one or more segments out of order, 17.619 to 19.042. And the R is relative, so we're in a view with relative sequence numbers. So this was going to be a quiz. What's missing? The answer's here. What's missing is the byte stream up to where the cumulative ACK is missing until we get to the left edge declared in the SAC. And there's some animation coming up where we'll look at this in more detail, because I want you to be really comfortable with the concepts of left edge, right edge. For me, it was like, I don't get that. That doesn't make sense. Left edge, why are they talking left and right? And we'll see some examples of why it's called that. So here's an example where there's two blocks of segments that have been received out of order. Two separate contiguous blocks that are also out of order from each other and out of order from the cumulative ACK. So you can see SAC count is 2. And now I've got 2 left edges and I have 2 right edges. This format is not really the best. We're going to look at a different format in a second, but not having changed our profile, there's 2 left edges, 2 right edges, and I think I have, yeah, I blew this up so you can see it better. So inside of the options field, you can see that, okay, now the count value is 2, saying I have 2 declarations of SAC blocks that have been received, and there's a left edge, right edge for the first one, and a left edge, right edge for the second one. The good news is you can display this more conveniently in Wireshark here by separately putting left edge 1, right edge 1 as columns and left edge 2, right edge 2 as columns. Great feature. And the way you do that is you'll edit the column header. Hopefully everyone's familiar with how you edit columns, right? Right mouse click on the header. You'll get this, you'll get title, type, and then fields. And in some of the fields, you'll get occurrence as an option. So now I can say, okay, I want the occurrence number 2 for the left edge. And that's how we got left edge 1, right edge 1, left edge 2, right edge 2. I'm just going to go back a slide to make sure that that's clear. So notice for this packet where there's only one, where the SAC count is 1, notice there is not a second instance. Make sense? But where there is 2, there we see both of them. And we said how many possible blocks could be declared in the options field? We could do 4 unless we have timestamps. In this case, there's 3. So you could actually, the only thing bad about, for me, using Wireshark and the flexibility of the columns is my monitor is not wide enough. I would love like a monitor that's like this wide, because then I could put all the columns in there. So you could, in fact, put instance 3 and instance 4 if they're present. Okay, pop quiz. You guys ready for a pop quiz? What's one of the best things about Wireshark? Say it again. Free. Open source. Come on, there's more. From each person. Okay, I was sure someone was going to say the developers. So this is one of my favorite things about Wireshark. It's the developers. And you've had a chance to meet them, hopefully. They have the nice gray shirts that says core developers. Please meet Gerald. If you have not met Gerald, please meet him. Take time out, meet him, say hello, let him know how much you appreciate this project and what it means to you in your workplace. So, yes, the developers, but what else besides the developers? For me, it's the totally flexible columns, views, and profiles. I mean, having a profile that changes color, changes columns, you can turn on and off different features in your profiles. You just move to the new profile, boom, it's like having a different instance of Wireshark. Very flexible. How many folks have actually met developers during the visit? That's almost everybody. We got a couple of stragglers here, you know. And it doesn't have to be a complicated discussion. It could just be, hey, thanks for what you do. That's easy, right? And they'll say you're welcome. Okay, time for an illustration of the left edge, right edge, what happens when something arrives out of order. So we're going to start with a simple example, and then we're going to go into a more complex example after this one. So let's assume that the sender transmits a burst of 5 packets. Easy to do math. I love easy math, so I made the length fields 10. Easy to work with. So we've got packet 1, 2, 3, 4, 5, sequence numbers 11 through 51. But there's a network issue, and packet 3 comes in last for whatever reason. Okay? So 1 arrives, 2 arrives, then 4 and 5, and then 3. So what does that look like from a SAC perspective? So the first 2 packets arrive from bytes 11 through 30. And then packet 4 arrives. Now I've got this gap between the cumulative ACK and what was just received. So the gap is in here. And of what I received, the left edge is in the byte stream count is at 41. And the right edge is 51. Meaning after the next byte I expect after this segment is 51. I did receive up to 50. So it's the same kind of math as the cumulative ACK. It means here's what I'm expecting next. Okay, so you have to subtract 1 to see what you have received up to. So we've got this little missing piece. Packet 5 arrives, and notice that the left edge has not changed, but the right edge has changed, because now I've got more stream bytes tacked on to the right-hand side. But I'm still missing the middle. Packet 3 finally arrives, and now we have a complete stream. All the segments have been received in order. We have to be reliable. So we're going to look at this now from a TCP perspective, but I'll just stop here for a minute and ask any questions about this before we go on. We will be talking about left edge, right edge quite a bit. Okay, so now let's look at some. Isn't that a beautiful watch? You ever wonder what's inside of a watch? These days it's usually just a little chip, but this is what was in there before the chips. I don't know how they did it. It's layers and layers of wonderfulness. So let's look at some mechanics now from the receiver side. So the first so you guys check me out here, make sure that I did this correctly. Don't assume that I know what I'm talking about. If you see something that sounds like that can't be right, then just raise your hand and say the words, wait a minute, that can't be right. And then we can discuss. So packet 1 arrives. The receiver starts a delayed ACK timer. Hopefully that's accurate. And now we're waiting for a second packet. Right? So quick side question. What happens when that delayed ACK timer gets to 0? We send an ACK, yeah. Unless we get another packet, right? So here comes packet 2. We cancel the delayed ACK timer because I don't need it anymore because I ACK every other packet, right? And now I ACK 31, which means I'm ready for what? I'm ready for byte 31 in the TCP stream. Thank you. And then you can see up at the top, so this packet came in. Packet 2 came in, sequence number 21, blah, blah. We send this ACK. Now things get a little more complicated. So packet 4 arrives, but it's out of order. So now what do I got to do? Well, I have to immediately issue an ACK because that's the rules. I have to say, hey, I received something, but it's out of order. It's not what I was expecting. And in the TCP options field, we're going to insert a SAC block that says, where's my button? There we go. That what I received was starting at 41 up to 50, and 51 would be the next byte after that. And oh, by the way, I was waiting for 31. So far, so good? So now packet 5 arrives, but it's also out of order. It's still out of order because I'm still waiting for 31. Anything that I get as a receiver other than 31 is considered out of order. So it's out of order, and now notice that what edge is this? Right edge? Yes, the right edge. And this is kind of an important point here that I don't always think about as much as I should. At this point, I'm holding on to 2 packets I can't get rid of. Why can't I get rid of them? Say it again. We're missing one. They have to be delivered in order because I made that promise, right? Reliable delivery, in order, using, so good. So far, so good. Now packet 3 arrives, and now we can say, hey, I'm ready for 61. So now I've signaled to the sender, I've received everything up and including 60, and I'm ready for 61. And the sender is aware that we receive things out of order. Now, whether the sender acts on that or not remains to be seen till we get to a more complex example. I have to do a time check. Are we on until 12:30? Is that right? Okay, good. Okay, so order has been restored to the force, and if you've never seen Lego Star Wars. I highly recommend it. It's a lot of fun. So, little shout out there to Lego Star Wars. So order has been restored to the force. So this one's going to be a little bit more complicated. We're going to take the principles we just looked at. It'll be a little bit more complicated. Before we start on this, everybody okay so far? And I hope you're patient with me. I'm starting slow for a reason, because it can get very complicated very quickly. And it's really good to anchor on some of the simple basics to say, okay, I got the basics. Let's see how we apply it to the more complex. So 6 packets now, but they arrive. We have a really bad network problem this time. And by the way, it's not a bad circuit, it's not a bad transceiver. When we say, oh, it's the network, it's a network problem, this is something that can't seem to put things out in the order it was received. So it's a network device issue. So now you can see we did 136, 452. I purposely made this as much out of order as I possibly could for the example. Okay, so this I should be able to move through this pretty quickly, I think. Packet 1 arrives, plain and simple. Packet 3 arrives, we've got a gap, right? Hey, we really want 21, but I did receive this. Cool. Packet 6 arrives. Uh-oh, things are really bad now. I've got 1 gap, I've got 2 gaps, I've got 1 contiguous group and another contiguous group that I did receive out of order. Let's check the math. So I'm still waiting for 21. Can't do anything until I get 21. I can't push it up to the application. I got to hold on to it, I got to buffer it. But oh, by the way, I have 1 segment, 1 group of segments from here to here, 31 to 41, and I have another group of segments, of bytes, sorry, stream bytes, from 61 to 71. So I've got 2 right edges and 2 left edges, okay? Here comes packet 4, which fits nicely right into this spot. And look what we did with this declaration. We bumped up the right edge of this one to say, hey, I went from 41 to 51. This has not changed, and this has not changed. I'm receiving data, but it's not in order. I'm still waiting for 21. So here comes packet 5, and notice that 1 group disappeared now because I was able to fill it in, and now this is contiguous. Does that word work, contiguous? Continuous? I'm not sure if that's a good word. Does that make sense, contiguous? Yeah? So it's all together. So I'm still waiting for 21. I have received this much, but I still can't do anything with it. So let me, pop quiz time. How many packets are in the sender's retransmit queue? So now we're thinking about the sender now. Sorry. How many? They're in the retransmit queue. I hear 4. Anybody else? You like 4? 1? 1, 2. We're getting all the options here. Except for the right answer. Actually, you know what? I think it is 4. I think it is 4 because we said we did receive this one, right? But I received 1, 2, 3, 4 that I can't use and that the sender might have to resend. So they're still sitting in the sender's retransmit queue because they have not been ACKed from a cumulative ACK perspective.
Well, you have told them by SAC that you have.
Yes.
The only one that the sender does not know is the white space up there and the one that just arrived, number 5, because you haven't acted yet. So the sender has not received an ACK from number 5.
So it sounds like there should be 5. So here we're gonna look at something later where we're gonna learn that just because we say that we sacked it doesn't mean that later on we won't run out of memory and we'll have to flush buffers and we might have to renege on that declaration. And that's actually in the RFC, reneging. So this one, so it should be 5 then. Whoops, what, come back. No, yeah. So it should be, I thought it was 5. I had to think about that, right? Because I sent this one, it just hasn't gotten here yet, plus these 4. So there's actually 5 in the retransmit queue, holding up memory. How many packets are in the receiver's queue that are stuck and I can't do anything with it? 4. Okay. These are, I know these are like really basic building blocks, but it's so important to get the basics right, because when you see the total chaos of how much chaos can be, you have to stand on these foundations. Okay, here comes in packet 2 finally, and now the SAC is gone, and we say we're ready for 71. So everything is now back together again. So we looked at 2 examples. We looked at account, the idea that there's a count. We looked at there's, for each instance of SAC, there's a left edge and a right edge, and these are different from the cumulative ACK. So far, so good? Okay. Yes? So that's a good question. So sorry, the question was, shouldn't there have been a retransmission after 3 duplicate ACKs, right? Because if we go back, we sent, there's 2 on this page, the first ACK, and there's duplicate number 1 at the bottom, that's dupe 1, okay? And then dupe 2, so let me point. So here's the first ACK. I'm having problems with my fingers here. Okay, here's the first ACK. Here's dupe number 1. Everybody agree with that? Here's dupe number 2. And here's dupe number 3. So, yes, he may do that. He may retransmit 21. So that's a good point. That's a good point. And it may show up later, because we know the 21 is already on its way. I mean, for this example, 21 is already on its way, and it does finally arrive. So we might actually get another copy of 21 if the sender retransmits it. Okay. So that's a good point. Thank you for bringing that up. Yeah. Any other questions, comments? Is it useful to visualize some of these concepts other than just the decodes? I mean, for me personally, I have to see something. I'm a visual person. My wife is different. If I need to explain something to her and I start to draw a picture, she says, no, stop. I don't want pictures. You have to tell me in words. I can't process pictures. So we're very different, and it's okay. So let's talk about some firewall effects that you might encounter. Some of these are a few years old, so you might not see them, but you might come across some older firewalls that randomize the starting sequence number. So if we're going through the firewall, I enter the firewall with sequence number 200, but when I leave, it might be 527, some random number. Has anyone seen that behavior? Randomized? Cisco ASA firewalls did that by default. I don't know if they still do, but it was a default setting. So it can cause a little bit of problems with SAC, because the receiver only knows what arrived at the receiver. It doesn't know what the original number was from the sender. So let's see what that looks like. So when those ACKs come back, I've got a picture that'll make this better. So what we're trying to understand is it possible that the firewall might make the SAC field unusable? That's what we're about to look at. So let's see that. So here's an example where the sequence number that's in the SAC field looks nothing like the sequence numbers that are in the header. So let's blow that up a little bit, make it a little easier to see. So notice I went through a firewall, the receiver created a SAC field. I went back through the firewall. The firewall put the original sequence, the original, how do I say this? Using the original starting point of the sequence number when it first came in, restored the numbers the way they should be, but what the receiver saw was something quite different and is using quite different numbers. Yes, sir. We would like that, wouldn't we? And I think some of the modern firewalls that do sequence number randomization will probably do that. But I think what happened is the ASAs came out before this RFC came out, and then it was a matter of catch-up. So it really depends on the version of the firewall, the vendor, et cetera. And maybe there might even be some options about, no, I don't want to do it. Yes, I do want to do it. But if you see this condition, then you know there's something in the path that's messing with the sequence numbers. And chances are, as somebody who's sending data, and my receiver signals back to me this information, I'd have to look at it and I go, I don't know what that is, because it doesn't match anything. I'd pretty much have to ignore it. I wouldn't really have a choice. Okay, so we looked at some basics. We looked at firewall. So now we're ready to have some adventures from the field. This will take about maybe 10, 15 minutes. But I want to share with you that concept of how bad is bad, because I came across something that was beyond bad. It was bad times 2, bad times 10. It was really bad. But that does look kind of adventurous, doesn't it? Wouldn't you like to take a safari like that? Open Jeep, nature comes to you. Wouldn't that be fun? You get a close-up photo. Okay, so we're going to look at an actual engagement. I was called in to a lab activity where and I'll just explain it through these slides here. So the customer was in a performance testing lab, and what they were testing is they wanted to test their new auto provisioning and server build process. You guys have heard of Chef and Puppet and others, right? There's more out there, Chef and Puppet. These were the early days of Chef and Puppet. So the client is actually a bare minimum host reaching out to the provisioning server saying, hey, provision me, build me, make me whole, right? I only have enough to reach out and ask for the bits and pieces. And the performance in the lab was so bad that they were unable to green light the migration. They had to put it on hold. Said, there's no way we can go live with this. It's that bad. Just building the server took like hours. It was ridiculous. So they said, come in, help us out. There was some non-technical issues. I don't know if you guys encounter these as you're doing performance when there's multiple vendors involved, right? Each vendor goes, hey, it's not me. My stuff's working great. It's those other guys, not me. So my challenge was to help the customer figure out why throughput is so slow and help them identify which vendor is actually causing the problem, right? So here's what we had in the lab. We had a concept of something called the public zone. These names don't really mean anything. This is where the server was going to spin up and needed its configuration. So the bare minimal, just enough of a server build to reach out to this server, the provisioning server, which had the details of what packages to push down, what patches, what applications. So basically, I'm going to send you your complete image based on the role you have in the data center. So the client wakes up, says, hey, provision me. The server then starts to send tons of data down to the client so that it could build. I think it was Puppet at the time, if I remember right. But for some reason, they're in two different security zones. Do you guys hear that terminology often, security zone? It's like things happen in here, there's a boundary, it's secure, there's firewalls, it's important concept in security. There was some fake latency generation in here, not a lot. 2 firewalls, 2 IPSs. So IPS in this zone, IPS in that zone. To me, that looks like a lot of security, right? Now, they were trying to mimic in the lab what would be put into production eventually. So that's why they had all this gear. And then we were taking captures off of the switches closest to the client, and then another capture over here closest to the server. So let's take a quick look at some visualization of some high-level metrics before we dig into some of the decodes. So this is not Wireshark. This is another tool that we use when we do some of these engagements. I'm showing it just to give you an idea of some higher-level analytics. By the way, this is a wrapper around Wireshark, so this doesn't work without Wireshark. So this breakdown here is, okay, so I grabbed some packets. There was millions of them, as you might imagine, and I came up with the idea that I can't look at everything all at once. Let me zoom into a small portion. 3.5 seconds. This purple means that more than half of the delay has to do with protocol delay. So that tells me right away I got something going on that's not about, that's involving TCP, protocol issues. And then over on the left-hand side, there's some statistics around, well, how much data did we move in that 3.5 seconds, and how many retransmissions, out-of-sequence packets, and triple duplicate ACKs. So we could have stopped there and said, you got protocol issues, and would have been right. But the idea was they had to figure out, and they already knew, hey, there's a lot of retransmissions, but we don't know why. So we had to dig a little bit deeper to help bring the vendors to the table and figure out who was playing a bad card. Because somebody who said they were innocent was not innocent. It just happens that way. Okay, so let's take a quick look again. We talked about bytes in flight. Let's talk about what does this metric tell us, because it's kind of important to our discussion about performance and why things took so long. So can I ask the room to kind of help me define bytes in flight from a Wireshark perspective? Perfect. How much data we've sent, so it's outstanding on the network, but from the sender's perspective, I haven't received an acknowledgement back, so they're in flight. I don't know if they got there or not. It's a mystery. It's unknown. So this is me saying what you just said, but you said it in fewer words, so I like what you said better, right? But I did have to put in this concept of the leftmost edge, just so that we have that as a concept, because we're talking edges here. And here's a picture. Oh, by the way, there's no real measurement of the congestion window, other than we can observe from the data, we can get a sense of, is it growing, is it shrinking? So it does reflect indirectly the congestion window. If fewer bytes in flight suggests to me that, oh, TCP, the sender is shrinking the window. He's not happy with the reliability of the network. We're going to shrink the congestion window. So you can kind of infer a little bit about the congestion window from bytes in flight. So here's our left edge defined. So let's say we burst 6 packets out the door. When we say it's the amount of traffic outstanding until we get the ACK, we're looking to ACK this segment here, right? So the left edge, that's why I put the left edge into that definition. So another quick look at this visual, because on the top, we're looking at what Wireshark would show as a graph of bytes in flight. And in here, we're just looking at traffic moving between 2 hosts, client and server. But let me zoom into a couple of these. So if you see a graph of bytes in flight that looks like that, what does that tell you? So we got packet loss, slow start. Something is happening where the sender is, okay, let's say this is the beginning of time for this burst. So we're gradually increasing the amount we put on the network. So we've got slow start at the beginning, which is how we make sure that the network is reliable to begin with. So I start slow, I see, can I get one segment out? Yeah, that looks good. Now let me double that. Did that work? Yeah, that looks good. Let me double it again. Did that work? Yeah, that looks good. So we see the bytes in flight going up, and then something bad happens in this block. This is traffic moving. Something bad happens, and now bytes in flight goes back down to 0, right? So we can see slow start going up, bad things happen, the network, I should say, the sender believes the network is unreliable. The network might be really reliable, but the sender believes it's not, so backs off. Why? Because I don't want to make things worse. If I keep growing and bursting, and everybody does that on an unreliable network, it just melts down. So all TCP stacks back off and say, I won't be part of the problem, I'll be part of the solution, I'm gonna calm down. All right, so we see two instances of ramping up, dropping down, ramping up, dropping down. And these gaps in here between the colored bars, those are idle time where nothing is happening. So productive time where I could be transmitting, I now have to wait because the network, I believe the network is not reliable. So I'm backing off, me the sender. So here's another view, we can see that happening again. And then we finally get to a point where, well, it doesn't back down to 0, but it never really gets to this peak level here for some reason. So that could be the sender just saying, you know, it's just not a good day, I'm just not going to get to a peak, I'm just going to keep backed off. So there's a great session called TCP congestion control. That's where I think there's more detail in that course about congestion control. But this is what it looks like when the congestion control algorithms say, hey, I've got to back off because the network is not reliable. Any questions about that? Because we're going to apply bytes in flight. Yes, sir. Sorry, that one?
Yeah. Couldn't that just be other traffic on the line?
No, this is actually, what we're looking at here, that graph, is the conversations between these two hosts in terms of what I can, of bytes in flight. So we're looking at congestion window shrinking and expanding and shrinking. So could it be because of other traffic on the network is your question, I think, right? To some extent, yes, it could, like especially if there's a flood of traffic and now that the network is like totally unreliable. In this particular case, we're in a lab and there's only these connections happening. There's nothing else. So, but you're right, in the real world, if the network becomes overloaded, the sender detects that how? Through triple duplicate ACKs, through the SAC field, shrinks the window and backs off, right? Because we don't want to be part of the problem. We want to be part of the solution. By the way, I've never used those words before with TCP, but I think it fits, right? We don't want to overload. We don't want to further overload the network. We want to calm it down a little bit. That's why we shrink the congestion window. Does that help? Yeah? Any other questions, thoughts before we move on? So we've kind of looked at the concept of SAC and edges, left edge, right edge. We looked at bytes in flight and how that affects or reflects performance, application performance, and throughput. So let's look at now the example of digging deep into the packets and seeing what was really going on during a portion of that 3.5 seconds. So we're going to use something that I call time-lapse photography, loosely, some animation, and we're going to step through a 19-packet burst. It'll be pretty quick. We'll do the first couple slow, we'll talk about them, then we're just going to look at it in more detail. The reason is that I put this together is because the number and the nature of the out-of-sequence packets is unbelievable. And there's no way to visualize it, at least for me, from looking at the decodes. From the decodes, you can see, yeah, it looks pretty ugly. But how ugly is ugly and what does that pattern look like? I had to take it to another level, and I thought it was a great example of how to illustrate and interpret SAC. So that's why it's in this presentation. So a little bit of orientation before we get started. So these are the ACKs from the client. So remember, the client is the host that says, hey, build me. I want to be a server one day when I grow up. So, hey, provisioning server, send me down my image, right? So these are the ACKs that came back from the client, and I have a couple of questions about these. First question, why are there so many ACKs? I thought I'm only supposed to do every other. Out of sequence. So everything is out of sequence. Everything coming is out of sequence. We'll see how bad in just a minute. Why does the packet size change between the numbers 66, 78, 86, and 94? Say it again. The length of the options field, yes. So down here at the very bottom, when we put Humpty Dumpty back together, there's no SAC here. Here's 1 SAC block, 2 SAC blocks, 3 SAC blocks. And we'll look at those in more detail. But those numbers tell me right away that, hey, there's SAC everywhere. And not just one block, but multiple blocks, which means lots of discontiguous blocks are being received. Third question, why is the receive window continuing to shrink? Because the receiver has to hold the data in his buffer. That's exactly right. And we know what happens when that number gets to 0, right? Everything stops. It's like, there's no more room at the end. Don't send me any more data. If you send me data, I throw it away. And look how we went from 44K down to 17K. By the way, is window scaling enabled by this receiver? We have a no. Do we have a yes? We have another no. So notice the double less than sign. So we have a scaling factor of 7. So window scaling is in play. But even with window scaling, I started out with only a 44K receive buffer. Now, potentially with the window scaling, I could have gotten up to a huge number, but 44 is our starting point, 17 is our ending point. So we know, getting back to this question up here, why is the receive window shrinking? Because we have to hold on to these packets. We can't get rid of them. We can't send them up to the application layer. Yes? So yeah. So I love that reply. I'm not exactly sure why that says 7, but scaling is on. So, but you're right. When you examine the scaling field, it's a multiplier power of 2, right? Could it be 2 to the 7th? Because it's a scaling. Well, let's come back to that after we go through this, because I want to make sure I drill into that. And thank you for pointing that out. Okay, so we answered some questions about our ACKs. Why do we see so many duplicate ACKs? Well, it's kind of a redundant question because there's a lot of things that are out of order, to be sure. Now we're about to start our instant replay, so I hope everybody is ready for that. And the only way I can characterize this, if you've ever been to Disneyland, Disney World, or Disneyland Paris, there might have been something called Mr. Toad's Wild Ride. Anybody know that by any chance? Nobody? Not a single person in the room? Oh no. Well, I'll just tell you quickly that you get in this little buggy with your kids, because it's a kid's ride. You get in there with your kids and you're driving along, all of a sudden you turn that way. And now you're going that way, and it's in the dark with flashing lights and signs. And then you quickly turn this way, and then you turn. It's a wild ride. So that's what reminded me. Okay, so we're going to go through 19 slides. Again, it's sort of an animation. In the top, we're going to see which packet was received by the receiver visually. And in the bottom, we're going to look at the ACK and the SAC fields. And each slide represents a new packet being received by the receiver. So some quick orientation. First off, we've got the frame order as seen by the receiver. That's in the very left column. Then we have the frame order as seen in the server-side capture. So what I did is I extracted the two captures to Excel and then kind of put them together to put this slide together. We're going to highlight something in red as it's received. So we're going to be able to easily see what packet just arrived. It'll be highlighted in red. Then as we move through the animation, what was red will turn green, meaning it was previously received. Not the current slide, but it was received previously. So what's in green will be indicating what was received previously. We're going to have the TCP header and we're going to have the SAC field to look at as we go through Mr. Toad's wild ride. So are you guys ready? You will need to fasten your seatbelts. There's no harness to put over you, so we've got to fasten seatbelts. Focus on the cumulative ACK and the SAC values. Double check your understanding. Hopefully the building blocks we used earlier in the presentation will help kind of make sense of this and say, oh yeah, I think I get what's happening here. And we're starting in a burst, this 19 packet burst, where, and this is not relative, this is actual sequence number. This is the sequence number that the receiver's ready for. So if you kind of just focus on 6095, you'll see that. So our first packet has been received in this packet train. So the sender sent 19 packets. The first one that got to the receiver was this one. And notice that, hey, you know, we were really wanting to get 6095. That's what I was waiting for, but instead I received 991 through 438, so you can see 991, 439. So hopefully the fact that that's an 8 and that's a 9 makes sense to you. Let me pause there for a minute. It's a little bit weird to first think about it, but it's the way the math is done, and I think it makes it easier for the computer to subtract numbers, something like that. So our first packet received was this one, and we immediately ACKed it, saying, hey, this is what I wanted, this is what I got. So far, so good? Okay, let's look at what was received next. So what was red is now green, meaning I previously received it. And now what I got is this packet. So we're much farther down the stream now in terms of what the receiver got. So this is not a little bit out of order. This is a lot out of order. And notice that my cumulative ACK has not changed. I'm still waiting for 6095. That's where we started. And I have two SAC blocks now. I've got the one from up here, 991 to 438, which you see here. And then I have this one I just received, 679 through 9127. Notice that the order of these blocks is arbitrary. There's no reason that the first one has to stay the first one. It can become the second one. Everybody comfortable with that? So that's why I use the word arbitrary. I don't think there's a rule that says they have to maintain their order in the options field. Okay, let's look at packet 3. Here comes packet 3. So packet 3 says time to change your battery. Packet 3 is the first one that left the server. Good news is, look at this, batteries. I'll tell you what, the SharkFest team is on top of things. Bear with me. They're sort of on top of things. They're not AAA. Are these AAA? Oh no. Okay, don't go anywhere. I have AAA. Okay, so the third packet received was the first one sent. So again, you get a sense of these are not arriving just out of order. They're kind of like wildly out of order. And the story continues in this vein. And let's see how we did. Yay. Okay. Here comes the fourth packet. So notice the fourth packet kind of marries up with the first packet that we got. And notice how the right edge changed now for this first block. Make sense? So now this block starts at 679 and now goes to 575. So far, so good? Okay. So that's the fifth packet. Sixth packet goes back up and fills in a missing spot. So notice now our cumulative ACK is at 1887, which says, hey, I got everything all the way up to here. But, whoops, sorry. Yeah, but now I'm down to one SAC segment. So the SAC segment is adapting and changing based on the arrival order. So we're just going to kind of keep going through this. There's 7, there's 8. This is the first time now we have 3 different groups of 3 blocks, 3 SAC blocks that have been received. There's 4. We still have the 3. Did we go down to 2? It's still 3, but in this case, what got updated was the cumulative ACK because we added on to here. So 334. I'm ready for 335. It hasn't come in yet. Now we jump down to this block, jump back up to that, jump down to that one, jump back up, boom, boom. And then we're ready for the last one, which is actually in the middle, right? The middle one was close to the middle, was the last one to be received. And now everything is back to what it should be. So that's a lot out of order. That's an example of not just a little bit out of order, but crazy out of order. So something in the network is seriously mangling the order of the packets. We saw the 2 IPSs, the 2 firewalls, those are the suspects. So this looks like a buffer management issue. You guys are familiar with last in, first out? First in, first out. Last in. So these are like standard CS 101 buffer management strategies. I think this was more UFO. Or maybe it's just iffy. Any questions or comments about that 19 slide? Is it useful to see the insanity of it, the chaos, that's the word I should say, the chaos of how bad is bad, right?
What would have happened if there had been a 4th SAC? What would have been dropped?
And there's no room for it?
Yeah.
So that's a great question.
Have a place for 3?
Yeah, so let's say TCP timestamps were enabled. So now I can only do 3. So the answer is I'm not exactly sure. But I have to guess there's no way for me to signal that I just received something else out of order. So I definitely have to ACK it, but that ACK may not possibly, nothing could possibly change, right? I couldn't, would I modify the currently defined things or not? I don't know.
You would probably just resend the last ACK, wouldn't you? Because you'd have to act like you didn't get it.
There's no place, yeah, I received something, but I can't tell you what I received because there's no place for me to put it. That's what I think would happen. But I would have to refer you to the RFC to be sure, yeah. Okay, so what was the outcome from this work? And it was, creating that 19 slide thing, that was a huge pain. It was not easy. It was like, wait a minute, what am I looking at? Does this even make, I had to kind of validate, did I put it together right? It was just so messed up. But the client was super pleased because we could help them show to the vendors that something's super broken. Not just a little bit broken, but super, super broken. We could clearly see the impact on the congestion window, and the client's position was, I've got to rethink these IPSs because they're killing me. They put the IPSs in bypass mode, and guess what? The problem went away. They were able to do their work. Now, the IPS vendor says, well, that doesn't make any sense. It can't be us. We do everything perfect. And it's like, well, let's look at this 19 slides together. And the guy's looking at it and he's going, that's not right. How did we do that? How did, and it stimulated their thinking about, man, we got to take a look at our buffer management strategy. Because it's not going out the order that it's coming in. And if you think about what an IPS has to do, it does have to accumulate many packets together and look for signatures. But there's no reason it can't send them out in the right order, hopefully, right? Okay. Oh, we're almost out of time. So I just mentioned that. We tested later. It was better. Still not perfect. There's some. I will finish at 12:30, by the way, maybe 12:31. The rest of these slides kind of summarize some of what we've already discussed. You wouldn't necessarily think out-of-sequence packets would be a throughput killer, but there's certain conditions where it can be. And that's why it's important to be able to understand how to interpret the SAC field, what does it mean, and help figure out how bad is bad. Again, there's a lot of shoulds and mays in the RFC, so it would be helpful to make a cup of tea, print out the RFC, or get it on your laptop and sit down in a comfy chair and just browse through it. So the sender, we saw some behavior of the sender. We saw the behavior on the receiver. We've got to buffer all those sequence. We saw receive window going down, 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 down. I think if that had been a 30-packet train instead of a 19-packet train, we probably would have gotten to a window size of 0, possibly, because it just kept going down. I mentioned this earlier. This is in the RFC. Data receiver reneging. So even though I sack something, I think that was your question, wasn't it? Yeah. Even though I sack something, I can go back on that. If I run out of space, I have to discard something. Maybe it's the new thing, but it could be an older thing. But something will get. The only promise is the cumulative ACK. If the stream byte is included in the cumulative ACK, it's guaranteed. Right? Even though I may not have actually handed it up to the application yet. From the TCP perspective, I've done my job. It's in sequence, I'm going to hand it to the application. TCP segmentation offloading. Has anyone heard of that? Also known as large send offload, right? So this is one of those things where who's really doing the resending? Is it the NIC? Is it the operating system on the sending side? So the question is, how do I know how do I know which component I need to focus on to see if they're complying with the RFC or not? So it could be the NIC, it could be the OS. TCP chimney, has anybody heard of that? Painfully? It's like, chimney, what the heck? That's a Microsoft thing. Different NICs have different drivers, have different versions, can behave differently depending on what features you enable. Some of the simple ones are checksum calculations, large send offload, large receive offload. Those are all possibilities. ESX could play a role because it has the physical NIC. All the VMs have virtual NICs. So who's really doing the work? So let's wrap up. So quick reminders, you can set a filter for tcp.options.sac.count and quickly find out how much SAC you have. You can also sort by packet size and you'll see different ACK packet size. It's so easy to add the SAC columns to the GUI. It's like, you don't even have to think about it, just do it, it's wonderful. Those were the examples that we looked at. Firewalls could have a play if you see SAC numbers that don't match the cumulative ACK. Something like a firewall has probably got randomization turned on. Focus on bytes in flight. That's really the golden nugget. If bytes in flight stays high, there's not a performance issue. There's really nothing to fix. It's good to know that, okay, there's a little bit of out of sequence, but it's not impacting anything. So focus on bytes in flight. We saw in our example in the lab how we kept doing slow start over and over again. We'd try to get some momentum, we'd fall back, we'd start over again, we'd fall back. This second bullet about it's easy to get lost drilling into the SAC, I was lost for days. My wife had to come find me. She says, "What are you doing? Where are you?" "I don't know, I'm in the SAC wonderland." So just, focus on bytes in flight. It's good to know the details so that you can kind of test your understanding and feel confident that, yeah, I understand this stuff. It makes sense to me. I can apply it. But I'd say don't get too lost drilling into it. And I think we're getting to the end. So if you see 3 or 4 gaps, so a SAC count of 3 and 4 means there's lots of blocks of things that are arriving contiguously, changing out of order. 1 SAC, 1 gap, probably not going to be a factor. Check bytes in flight. And then that's it. So thank you everyone for attending. Hope this was useful. Thank you.